Hello ib3 students, my next video lesson about engineering physics. Yesterday we were talking about torque, so short revision to all of you about the torque. So what is a torque? Torque is a product of force acting times arm times sine of the angle between direction of force and direction of the arm. So when you have a pivot, so point of rotation, okay, and you have a kind of, let's say, rod or something, yeah, and let's imagine that this rod has no mass and you have a force which acts on this rod. A vector of force makes angle alpha with the this rod of, let's say, length r. Then then torque is given by F times R times sine of this angle alpha. Yeah, and we've used torque yesterday to find the rotational equilibrium of the bridge and of the wooden desk or wooden rod staying on the two supports. Do you remember this? I hope yes. And I hope that today you are also prepared to the lesson. So pen, pencil, ruler, your physics notebook and powerful calculator. Thank you for writing present. Of course, present must be written in your Google Classroom below this lesson, not in the YouTube channel. Is it clear? In the Google Classroom. Okay, so let's do one more exercise related with this topic, and then I'm going to talk a few words about moment of inertia. So let's imagine another example. You have, again, a uniform rod, yeah, which is placed on two supports. So support 1 and support 2. Okay, and there is, let's imagine, let's complicate situation a little. Let's imagine that there is an object, a point object of mass capital M. Yes, the point object of mass small m, and rod has a mass of m. And this capital M is given like, let's say, 200 kilograms. Small m is given, let's say, 100 kilograms. We have length of this rod. This rod is L. It will be easy if it's, let's say, 10 meters. Let's of course use G as 10 meters per second squared. And let's imagine that first support is located at distance R1, which is equal to 1 meter from the left end of the rod, and support 2 is located at distance R2, which is equal to 3 meters from the right end of the rod. And your task is to find the distance between the left end of the rod and this mass, let's name it x, for which forces exerted by these two supports are equal. Okay, so force created by support 1 must be equal to the force created by support 2. Is that clear? So again, we have a rod which is supported by two supports. Distances are given: the length of the rod, distance of the support 1 from the left edge of the rod, distance of the support 2 from the right edge of the rod. We know mass of the rod 200 kilograms and mass of the object placed on the rod 100 kilograms, and you have to find position where this mass should be placed, this object should be placed, to equally spread overall force on these two supports. So force exerted by support 1 must be the same as force exerted by support 2. Please copy this. It's not easy but not too difficult. If you remember what you did yesterday, you have to solve this problem in, let's say, short time, let's say 10 minutes, yes? So copy this. Please stop this video for maybe more, maybe 12 up to 15 minutes, and try to solve this problem. After, let's say, 15 minutes, I'm going to give you solution, and then, and you will copy this, I'll be sure that you are ready for moment of inertia. Is it clear? So please copy this. Stop video, copy this, and solve this. Okay, after 15 minutes. What do we have here? Again, you have to build two equations. One equation which is related with a balance of with translational equilibrium, so all forces acting down. This one, so Fg, let's say 1 for the object, and Fg, let's say 2 for the rod, must be balanced by two supports. This one, Fs1, and this one, Fs2. Is it clear? Okay, so what is the first equation? Fg1 plus Fg2 must be equal to Fs1 plus Fs2. Okay, so let's look. By using this equation, you can calculate force of each support. Is it clear? Because if Fs1 is equal to Fs2, you can write this in the form of mass of Fg1, 1 is small. Small mass times g plus huge mass times g must be equal to times Fs, because Fs1 is equal to Fs2, so I'm going to use Fs. So what do we have? Small mass 100 times g 10 plus huge mass 200 times g 10 is equal to 2Fs. It's 2Fs, not Fg, Fs, of course. Okay, so we have here 1000 and 2000, together is 3000. 3000 divided by 2 is 1,500 of newtons. So by using translational equilibrium, we've obtained the force exerted by each support as 1,500 of newtons. Okay? And now, second equation for rotational equilibrium. So let's imagine that object is able to rotate along this pivot. Okay, so we know that this object doesn't rotate. This rod with mass doesn't rotate, which means that all forces are balanced. What does it mean? It means that momentum with effect clockwise must be balanced by momentum with effect of counterclockwise. How can we write this? So let's look. Momentum in the clockwise direction is given by only two masses. So we have gravitational force 1 acting on mass placed on the rod times distance, which is unknown, plus gravitational force 2 acting on the rod times distance, which is half of the length of the rod, because we have to connect this force to the center of mass, must be equal to torques given by supports. So Fs of first support at distance of r1 plus Fs the same at distance of L minus r2. This distance between second support and pivot is L minus r2. So there is only one unknown in this exercise, x, because Fg1 is given. Fg1 is 100 times 10 times x, of course, plus Fg2 is also given, is 200 times 10 times half of the length, is equal support 1, which is 1500, we've calculated this here, and distance of r1, which is 1 meter, plus support 2, 1500. Oh, I see small mistake, is L minus. I don't know what I said. I hope that I said minus. because the distance between pivot and support 2 is L, which is 10 meters, minus R2, which is 3 meters. Okay, so we have equation with one unknown. At the beginning I can cross two zeros, so 2 zeros here, 2 zeros here, 1, 2 zeros here, and 1, 2 zeros here. Okay, so finally we have 10x plus 200 times half gives 100 is equal to 15 times 1 gives 15 plus 15 times 7 gives 105. Okay, so 10x is equal to 120 minus 100 is equal to 20, and x must be equal to 2 meters. Oh, nice result. So when x is equal to exactly 2 meters, yeah, then support 1 exerts on the rod the same force as support 2. I hope it was not too challenging, it was not too difficult to you. If it was too difficult, please copy this. So let's stop video for, let's say, 5-6 minutes. Copy this to your notebooks, read this again. If you still don't understand this, please copy this again, read this again, and learn. It's not difficult. Okay, 5 minutes later. Moment of inertia. You can write this as a topic. Okay, what is a moment of inertia, and what is equivalent of moment of inertia, and how to calculate moment of inertia. Okay, moment of inertia has a symbol of I, okay, and is related with, again, rotation. Okay, its unit is kilogram times squared meter. Okay, so let's imagine that you have the axis of rotation, or maybe point of rotation, so something which is able to rotate clockwise, and at a given distance you have a point of mass m. So again, this is pivot, this is point we have to focus, and this point rotates, so moves along a circle. Let's imagine that this distance is r. So moment of inertia of single point mass, yeah, without diameter, without size, is given by expression of m times r to the power of 2. So moment of inertia is about the distribution of mass along point of rotation along pivot. So if you have object which has a shape, okay, let's imagine that you have an object like this, and center of mass of this object, yeah, rotates along this pivot, along this curve path, then moment of inertia of this object will be given as a sum of each point mass which creates this object times distance of given mass squared from the pivot. So you have to split this object into infinite number of small masses and calculate moment of inertia of each mass, and finally you have to add these momenta. But fortunately, for given shapes, moments of inertia were calculated by mathematicians. It's not too difficult. If you are good in mathematics, you can do this, you can try to do this. Moreover, it's very good topic for internal assessment in mathematics. Okay, so finally you can the momenta are derived for simple shapes like a disc, like a sphere, like a spherical shell, like a cylinder, etc., etc. Okay, so let's find this maybe here. Oh, so wait a moment, let's look in internet. I have maybe not good source, Wikipedia, But in this case, we have a momenta of inertia of simple shapes, like I hope, like this rod rotating, or like objects of different moment of inertia speeds. Oh, unfortunately, we don't have here, but of the sphere, of the this rod we have a thin disk. Okay, at constant thickness and given radius. We have moment of inertia of compound pendulum. Here is moment of inertia of disk of the sphere. Okay, 2/5 mr squared. So, and these momenta are given. So let's focus maybe on the picture which was presented here. So let's look. In this picture, you have few objects like a sphere, solid sphere. Okay, this one, the third one, like this kind of pipe, sphere which is empty inside, and first was a cylinder. So what is moment of inertia? Moment of inertia tells us what energy is needed to make object to rotate. So let's look. If you have few objects which are rolling down, in typical physical problems, when no moment of inertia is taken into account, we have simple transformation of energy from potential energy at the top of this hill to kinetic energy at the bottom of this hill, of this slope. With moment of inertia, part of this initial potential energy is taken by the rotation of the object. Rotating object has also own energy, and the source of this energy in this case is initial potential energy. So when initial potential energy, the part of this is taken to rotate the object, then kinetic energy of translation must be smaller. Is it clear? So this is the role of moment of inertia. Okay? So let's take a moment, let's do a simple example with moment of inertia of typical disk. Okay, wait. Here, moment of inertia of disk. Where is this? Definition, examples, a moment of inertia of a pendulum, compound pendulum. I'm looking for this. It's half of mr squared probably. This is for point mass. Examples. This is for rod of a thin disk of constant thickness and radius r. Okay, so this is half of mr squared. So let's imagine something like this. You have a disk, like here. Yes, a thin disk. Okay, of given radius and given mass, and let's imagine that this disk rotates along this axis. Okay, so moment of inertia of this thin disk is given by half of mass of the disk times squared radius. You can derive it in a simple way, but this is not your task now. And let's imagine that this disk is rotating with angular velocity of omega. Okay, so what is energy stored in this rotating disk? This energy is known as rotational kinetic energy. Okay, and the rotational kinetic energy is very, very similar to translational kinetic energy. It's half of not mv squared, but moment of inertia times angular velocity squared. Okay, so for typical translation, for typical displacement, kinetic energy is given by half of mv squared. In this case, we have very, very similar. So let's look. In rotation, moment of inertia is equivalent of mass in translation. In rotation, angular velocity is equivalent of linear velocity. And this constant is the same. You see? So kinetic energy, rotational kinetic energy, in rotation, and typical kinetic energy or translational kinetic energy in typical translation or movement. Yeah. So by using this and this, there will be your exercise now. Let's imagine that you have a disk of given radius. Radius will be not important, you'll see. Let's imagine that you have this disk, a cylinder, placed on the top of the slope of given height and given angle. Okay? And then this disk is released and rolls down the slope. Okay? Our task will be to find the linear speed of center of mass at the bottom of the slope. Is it clear? So please copy this, and our exercise is exercise 1. Don't take into account the moment of inertia at this moment, okay? So no moment of inertia. So we have simple situation. We have a simple slope of given height. Okay. And at the top we have a cylinder. Okay? And this cylinder rolls down, and your task is to find its speed down the slope. So let's imagine the top is a point A and down is a point B. And height is given, let's say 5 meters, and use G equals to 10 meters per second squared. Please copy this and use typical classical mechanics, the movement of energy transformations, to find speed of the object down the slope. So you have 5 minutes to do this. Start. After 5 minutes, of course, please turn video again and we will check your results, and I give you another problem, a better one, then you will see difference between situation with no moment of inertia and with moment of inertia. So start. Okay, 5 minutes later, yes? Okay, let's write this. 5 minutes later. Okay, so it's I hope it's simple because you have typical energy transformations. Potential energy at A must be equal to kinetic energy at B. So mgh must be equal to half of mv squared. You can cross m. Okay, so finally v is equal to the square root of 2gh, which is the square root of 2 times 10 times 5. Oh, fortunately, the result is nice because 20 times 5 is 100. So finally, the speed at B, velocity at B, is equal exactly 10 meters per second squared, assuming that G is equal to 10 meters per the speed at B is equal to 10 meters per second, of course, assuming that gravitational acceleration is 10 meters per second squared, and assuming that there is no rotation of the disk. Is it clear? Okay, now, okay, I hope you have this. If not, please copy. And exercise 2. Now let's take a moment of inertia of the disk. Moment of the inertia of the disk is half of mass of the disk times its angular velocity squared. I am not going to give you a mass, and I'm not going to give you an angular velocity. You have exactly the same task. You have a slope, yes. You know that object rolls down the slope from point A to point B, okay. You know that height of the slope is given, is exactly the same, is 5 meters. Let's use gravitational acceleration as 10 meters per second squared. Okay, And your task is to find the same speed of the object at point B at the bottom of this slope, but you have to take into account moment of inertia of the disk, so you have to take into account energy needed to make rotation of the disk. This task is more challenging, so please copy this and spend more time, let's say 15 minutes, not more. 15 minutes is long enough, okay? After 15 minutes, please turn video back and you will see my solution. Then you can compare your with mine. Is it clear? So 15 minutes, start. Okay, so 15 minutes later, yes? Okay, here, what do we have here? Again, energy transformations. Potential energy at point A, must be equal to kinetic energy at point B plus rotational kinetic energy at point B. We know that at point A, object starts to move. It doesn't have speed, linear speed, and it doesn't have angular velocity. It doesn't move, it doesn't, and it doesn't rotate. At point B, we know that center of mass of the object moves along the slope, and object rotates. It spins, so it has both and typical translational kinetic energy and additionally rotational kinetic energy. Okay, so mgh must be equal to half of mv squared plus half of I omega squared, because rotational kinetic energy is given by half moment of inertia times angular velocity squared. Okay, and of course we know these two equations. We know that I is equal to half of m. Oh my god, what I did here. Okay, r squared, of course, not omega squared. Sorry, I will write in the comment that example 2 I gave you equation half of m omega squared. It should be given a half of m r squared. Oof. So I hope you will read comment before. I don't know which minute it is, but I will check later. Okay, so half of m r squared, and second, you have to know, I hope that you remember from yesterday, that v is omega r. It will be needed, because then by using this you will be able to eliminate the radius which is not given. Is it clear? Radius which is not given. Okay, so let's make one equation. mgh is equal to half of mv squared plus half of I is half mr squared, and omega is v over r, so we have v squared over r squared. Due to this, you can cross r squared and additionally mass here, here, and here, obtaining gh left hand and half of v squared right hand and a quarter of v squared the right as a sum. Okay, so finally we have gh left and 3 over 4 of v squared to the right, obtaining equation for v as 4 over 3 gh the square root of. Is it clear? We can use data, so v is equal the square root of 4 over 3 times g, which is 10, times height, which is 5. So I have no calculator now, so I can use this in the form of 2 over 3 times 100, okay, so which is 10 times the root of 2 over the root of 3, which is of course less than 10. Let me calculate on my phone. Calculator here. So the root of 2, where is the root here? Yeah, I have the root of 2 divided by 3, the root, equal times 10, which is 8.16, so around 8.2 meters per second. So you see difference? In the case of no moment of inertia, speed is 10 meters per second. If we will take into account moment of inertia, speed is smaller, 8.2 meters per second. So you see that moment of inertia changes calculations. Is it clear? Okay. So now your homework. Do exactly the same exercise. But with, in example 3, solid sphere. So find moment of inertia of solid sphere. Okay. And in example 4, in the case, do the same with the pipe or sphere which is empty inside. Sphere which is empty inside has I hope we have this here somewhere. Oh, spherical shell. Okay, so find moment of inertia for a solid sphere and for spherical shell and do the same calculations, and you will see which object is the fastest, which object is the slowest, so in which case the energy needed to make rotation is the biggest and where is the smallest. Is it clear? Okay, so sorry for my mistake in the previous example. I will write before I will upload this movie, I will write this in the comment, and I hope you like this topic. Thank you for watching. Do this homework, learn physics, and stay at home. See you, bye.